A corner of a 22-story building disappeared in seconds. An entire corner, from the ground all the way to the roof, just gone. Nobody saw it coming. No warning, no structural alarm, nothing dramatic building in the days before. The cause turned out to be something a person carries in their pocket. A single lit match struck by a resident on the 18th floor at 5:45 in the morning. The explosion was so small that the person who caused it survived. Conscious, uninjured, still inside the building. But the corner of that tower? 22 floors of it collapsed in seconds, and when engineers looked at the wreckage, they didn't just find a building that had been poorly constructed. They found something far more unsettling, a design principle that was hiding inside thousands of buildings around the world, including in America. What they discovered that morning in London changed the way every skyscraper in the United States is built today. The building you work in, the hotel you stayed in last year, the apartment tower you pass every morning, all of them exist the way they do because of what one match exposed in 1968. This is that story. After World War II, London was in crisis. German bombing had destroyed or damaged over 1 million homes across the city. Entire neighborhoods had been flattened. And when the war ended, people didn't just need to rebuild. They needed to start families. The population was growing, the housing was gone, and the government needed a solution fast. The answer, they decided, was to build up. Tower blocks could house hundreds of families on a small footprint of land. They could be built quickly, and most importantly, they could be built cheap. The British government didn't just allow high-rise construction, they actively subsidized it. The taller the building, the larger the government grant. Build above 6 floors, get a bonus. Build above 15, get more. Build above 20, get the maximum. That financial incentive created a problem nobody was paying attention to. A construction system called the large panel system, originally developed in Denmark for buildings of 6 stories or less, was being adapted for towers 3 and 4 times that height. Large concrete panels were manufactured off-site, transported to the location, and bolted together to form the structure. There was no steel frame, no internal skeleton, just panels stacked on panels, connected at the joints with bolts and mortar, fast, cheap, and it required almost no skilled labor. And it had never been tested at 22 stories. Ronan Point was completed in March 1968. 110 apartments in Canning Town, East London. Residents moved in the same day it opened. The entire building had cost £500,000. For families coming from cramped Victorian terraces, the spacious rooms and central heating felt like the future. They had been living there for exactly 2 months when everything changed. If this is the kind of story you come here for, subscribe. New videos every week. Now, May 16th, 1968, 5:45 in the morning. A resident on the 18th floor walked into the kitchen to make tea. There had been a gas leak overnight from a newly installed cooker, a faulty fitting, over-tightened during installation, slowly seeping gas into the room for hours. The resident didn't smell it, didn't know. They struck a match. The explosion that followed was, by any measure, small. It was contained almost entirely within that one apartment. The resident was knocked off their feet and lost consciousness, but survived. No serious injuries. The stove itself survived the blast and kept working, but the load-bearing wall panels that formed the exterior corner of that apartment did not survive. The blast blew them out, and without those panels, the floor above had nothing to rest on. It collapsed. The floor above that went next. Same reason, same result. Then the next one. All the way down, all the way up. In seconds, the entire southeast corner of Ronan Point, every floor, every apartment, every wall along that corner from the ground to the roof, came down in a cascade of concrete panels. 5 people died, 17 were injured. The building had been open for 63 days. The immediate question was obvious. How does a small gas explosion bring down a corner of a 22-story building? The answer came from how the building was actually holding itself up. In a conventional structure, loads travel through multiple paths, a frame, a core, redundant connections. If one element fails, the load redistributes. The building absorbs the loss and keeps standing. Ronan Point had none of that. The large panel system had no structural frame. The panels were the structure. Each floor rested on the walls directly below it. Those walls rested on the walls below them. The connections between panels relied largely on friction and gravity, not on engineered redundancy. Engineers described it as a house of cards. Remove one card, one panel, and there is no alternative path for the load to travel. It goes straight down, taking everything with it. The building didn't fail because of a gas explosion. The gas explosion simply revealed that the building had no way to survive losing a single element. It had been designed that way from the beginning. When investigators looked closer, they found something that made the original failure look minor. When Ronan Point was finally demolished in 1986, 18 years into a 60-year expected lifespan, engineers took the building apart piece by piece. What they found inside the joints and connections was, in the words of the architect who led the inspection, shocking. Approximately 80% of the structural bolts were missing. They weren't damaged or loose. They simply weren't there. They had never been installed. The joints that were supposed to be filled with load-bearing mortar were found packed with newspaper, cigarette cartons, and pieces of cardboard. The building that the government had declared safe, reinforced, and fit for habitation. After the 1968 collapse had been standing for nearly 2 decades, held together largely by friction and luck. The inspector's conclusion was direct. Not a single joint in the building was correct. The system produced exactly this. Piecework labor paid by speed, not quality. Connections hidden inside panels, sealed before anyone could verify them. Inspectors signing off on work they couldn't physically see. One contractor cutting corners would have been a scandal. This was just the industry functioning normally. Ronan Point was the system working exactly as it had been built to work. By the time engineers understood the full scope of what had happened, the question was no longer about one building in East London. It was about every building built the same way. In the decade following the collapse, engineers published more than 300 academic papers and technical reports on a concept that had barely existed in structural engineering before 1968. Progressive collapse. The question they were trying to answer was simple. What happens to a building when it loses one structural element? Can the remaining structure absorb that loss, redistribute the load, and stay standing? Or does it cascade? Before Ronan Point, almost no building code in the world required an answer to that question. The United Kingdom didn't require it, neither did Europe or the United States. The assumption built into construction standards everywhere was that buildings would be built correctly and never asked to survive the sudden loss of a load-bearing element. Gas explosions, vehicle impacts, localized fires, these weren't designed against. Ronan Point ended that assumption. In the years that followed, the American Society of Civil Engineers rewrote its structural integrity standards. The American Concrete Institute updated its building code requirements. For the first time, American engineers designing buildings above certain thresholds were required to demonstrate that their structures could survive losing a single element without triggering progressive collapse. The concept had a new name in American engineering: robustness. A robust building isn't one that never gets damaged. It's one that can take a hit, lose a column, lose a wall panel, absorb an explosion, and stay standing while the load redistributes through alternative paths. That requirement didn't exist in American construction before 1968. It exists today because of what one match exposed in London. The engineering lesson of Ronan Point was learned. The codes were rewritten. The standards were updated. But the institutional lesson that buildings need to be verified, not just declared safe, proved far harder to teach. In 2017, a fire broke out in Grenfell Tower in London. 72 people died. The same question came back. How many other buildings? Investigators found towers built to the same methods as Ronan Point that had never been properly reinforced. Some were still connected to gas supplies, decades after Ronan Point had shown exactly what that combination could do. One independent researcher found over 1,500 towers in the United Kingdom alone matching the Ronan Point construction profile. The codes had changed. The habit of declaring things safe without actually checking them hadn't moved an inch. A resident on the 18th floor of a London tower block struck a match on the morning of May 16, 1968. They were trying to make tea. That match put a design principle to the test, one built into towers all over the world, and it failed completely. The corner disappeared, the engineers arrived, and for the first time the entire field of structural engineering had to confront a question it had never formally asked. What happens when one piece fails? The answer to that question is now written into the building codes that govern every skyscraper constructed in the United States. The next time you walk into a high-rise, your office, a hotel, an apartment building, that structure was designed assuming it could lose a wall and not collapse on top of you. It wasn't always designed that way. One match changed that, and the building you're standing in is the proof. If this kind of story is what you come to this channel for, subscribe. There's more coming. And if you want to go deeper on how buildings fail and what changes because of it, another one is right there.